Okay, so last time we talked about the reactions related to haloalkanes, and make sure you complete the questions, checkpoint questions. Afterwards, I will mark your answers on Google Classroom. Okay, so for this one, the most important part is that you remember the two mechanisms here. So SN1 and SN2. Okay, and this is a very simple representation of the two mechanisms. Okay, so one of them, it involves, so for SN1, it involves only one molecule to form the reactive intermediate. But for SN2, give me a second. For SN2, it involves two molecules to form the reactive intermediate. Okay, so that's the difference. So today we're going to see something similar to that, and we're going to move on to the reactions related to alcohol. Okay, so first, similarly, we can separate alcohol into different categories: primary alcohol, secondary alcohol, and tertiary alcohol. It depends on the position of the hydroxyl group. Okay, so if the carbon with the hydroxyl group is only attached to one more alkyl group here, then we say it's primary alcohol. Okay, so here we got an example: ethanol, only one methyl group to that carbon with hydroxyl group. Again here, one alkyl group attached to that carbon with hydroxyl group. Hence, we call this primary alcohol. And for the second row, we got the secondary alcohol. So here, we got this carbon attached to the hydroxyl group, but now we have two alkyl groups, R1 and R2. So this is called secondary alcohol. And similarly, if we have three alkyl groups attached to that carbon with hydroxyl group, then we call it tertiary alcohol. Okay? Okay, so quickly, let's go through the checkpoint question for the naming part. So first one, to which class does the following alcohol belong to? Okay, so this carbon is attached to the hydroxyl group. However, here we have three hydrogen. So which one should we choose to be the correct answer? Remember, we take a look at the carbon that attached to the hydroxyl group. If this carbon is attached to one methyl group, okay, or one alkyl group in R here, we say it's primary. If attached to two alkyl group, okay, then we say it's secondary. Three alkyl group, then it's tertiary. So here, this carbon attached to three hydrogen, so it doesn't attach to any alkyl group. So here, maybe you may guess it's this one, 0 degree. But remember, for alcohol, we only have from primary to tertiary. But this carbon is not attached to any alkyl group, isn't it? It's attached to three hydrogen. Okay, so for this one, that's a special case you need to remember. That's still primary alcohol. So methanol, that's a special case you need to remember. It attached to three hydrogen here and still primary alcohol, because we don't have any alcohol that got 0 degree. Okay, from primary to tertiary. Okay, remember, don't choose D because it attached to three hydrogen, not three alkyl group. Okay, so it should not be the tertiary alcohol here. So correct answer, please jot it down, it should be B. Okay, and then the next one, which of the following is a primary alcohol? Again, we're gonna look at that carbon attached to the OH group. Okay, so for the molecule for A, this carbon is a carbon attached to the OH group. Okay, let's check how many alkyl group it attached to. On the left hand side, we got this alkyl group. Okay, and then we got a hydrogen attached to it. And then we got another alkyl group here. Okay, so that should be a tertiary alcohol. Sorry, that should be a secondary alcohol. Okay, I wrote it correct, but I said it wrong. Okay, it should be a secondary alcohol. We use the same method to examine the second one. Okay, so this is a carbon that attached to the OH group. And on the left hand side, we got this alkyl group here. On the right hand side, we got this alkyl group here. And of course, it needs to be bonded with 4 bonds. So the other one left with is a hydrogen atom. So for that molecule, it's a secondary alcohol. Okay, take a look at the next one. Again, we find the one that bonded with the OH group, should be that carbon. And then take a look, for this carbon, it's attached to 3 alkyl group here. Okay, so it should be a tertiary alcohol because this carbon with OH group bonded to 3 alkyl group, so it should be tertiary alcohol. And let's examine the last example. Again, find the carbon with OH group on it. For this carbon, it's only bonded with another alkyl group. Okay, and the rest 2 bonds are with hydrogen atoms. Okay, so for this one, it's a primary alcohol. Okay, so the correct answer, we should choose D. Okay, any questions so far? Can we move on? Okay, so let's start with the reactions related to alcohol. When we talk about reactions related to haloalkane, we said that's a method to make alcohol. So today we're going to learn the second method to prepare alcohol, which is the acid catalyzed hydration of alkene to alcohol. Okay, so you can write it down. That's the second method to prepare alcohol. Okay, so the first one is turning haloalkane to alcohol. Okay, so that's the one we discussed in previous lesson. So what should we use for this reaction? First, you need to remember the reactant we use, which is alkene. And the product we get should be the alcohol. And here, we also need catalyst. Okay, the catalyst here we use can be concentrated sulfuric acid or concentrated phosphoric acid. Okay, and the condition you also need to remember, it only takes place on the high temperature and high pressure. Okay, and then here please note that the concentrated phosphoric acid is preferred compared to the concentrated sulfuric acid. Okay, because we know concentrated sulfuric acid has oxidizing ability. So it may have some side product formed during the reaction. Okay, so concentrated phosphoric acid is preferred as a catalyst for this reaction. Now let's take a look at what's going to happen for this reaction. Here we have 2 examples. The first one we have here is propane molecule. And after we adding the catalyst and then put them under the right condition, we would add the OH group onto the double bond, and of course we also added one hydrogen atom onto it. Okay, and the OH group will be added onto the more substituted carbon. Okay, what does this mean? So this carbon, you can see, only attached to this alkyl group. Okay, so we say it's primarily substituted. But for this one, okay, so it attached to two alkyl group, so it's secondary. Okay, so that's more substituted. So the hydroxyl group would attach this position. So the product it will form, it should be propanetolone, which is here. Okay, the hydroxyl group will attach to the second carbon. Okay, same for the second example. We have double bond here. So the OH group can potentially add on to this position. I use blue to represent, and another position I use red to represent. For the blue one, for this one, it has one alkyl group and two alkyl group, okay? But for the red point here, I highlighted, got one alkyl group, the second alkyl group, the third alkyl group. So we say the red point carbon here is more substituted. Hence, your hydroxyl group should be added onto this carbon. Okay, then you can draw the product as this. So hydroxyl group added to the more substituted carbon, and then hydrogen atom would add on to the other side of the double bond and give you the product. Okay, so why that would happen? Okay, this mechanism is not required. I just kind of show you what's happening in this reaction. So first, that's the catalyst we put in. It will provide the hydrogen ion. Okay, so the first step is to form the carbocation here. Okay, and then the water would attack this positively charged ion. Okay, as you can see, water here got lone pair on it, and it's attacking the positive charge. So that's nucleophile attacking the positive charge here. Okay, and then it will form this reactive species. We call it oxonium ion. So this name is given for an atom that the oxygen cation with 3 bonds. Usually oxygen only form 2 bonds. Okay, that's what we see in water molecule. It only form 2 bonds. When it forms 3 bonds and it becomes positively charged, then we call it oxonium ion. Okay, and then after forming this reactive oxonium ion, there are two, then the hydrogen will leave, and then will give you the alcohol it formed. Okay, so that's the reaction. This one pretty straightforward, but for this method to prepare alcohol, it has some pros and cons. So for this one, the good thing is a fast reaction, and we will be able to get pure ethanol product or alcohol product. And also, it's a continuous process. Okay, once we put everything in and get to the right condition, it will just continue by itself. But it also has some disadvantages. So first, you can see it requires high temperature and high pressure. So it requires a lot of energy input. Okay, so that's a downside. High energy input. And then for this reaction, it would require an expensive plant. So that's also a disadvantage. Okay, and finally, look at the raw materials we use here. Okay, it's alkene. Alkene we have learned is we get it from fossil fuel, which is a non-renewable energy. Okay, so that's also a disadvantages. Okay, so that's about the first reaction, the acid catalyzed hydration of alkene to alcohol. Now let's move on to the second reaction. It's substitution reaction of alcohol with halide. Okay, so in this reaction, you will see two types of reactants used here. It can be HX. So the X can be chlorine, bromine, or iodine. Okay, but the product would be similar. Okay, we use similar way to work out the product. So you can tell by its name, substitution reaction. Okay, so the halogen here, chlorine, bromine, iodine, would take the place of the hydroxyl group in the reactant so that we can draw the product. So for the first box, the first example, the product should be chloroethane. So the chlorine would take the position of the hydroxyl group. Okay, and similarly, we can work out the product for the second reaction. Bromine would take the position of the hydroxyl group, so it will become bromoethane. And the second one, it would become iodoethane. Okay, so on the right-hand side, we can use another reactant, which is PX3. So again, X can be chlorine, bromine, or iodine. And the product will be the same. Okay, so first one, we would get chloroethane. Second one, we will get bromoethane. Last one, we will get iodoethane. Okay. So for this two reaction, you don't need to write the other product. Just focus on the haloalkane that we produced in the reaction. Okay, and remember, for the condition, you need to heat it under reflux for this reaction to go to regenerate the haloalkane. Okay, and take a look at the mechanism. Again, this mechanism is not required, but it's related to the SN1 and SN2 reaction we have learned. So you better know that. Okay, so let's quickly revise what is reflux. Okay, so in the previous lesson, we have learned this setup. Sorry. Okay, it looked like this. That's the heating under reflux setup. So you put the two reactants in the round bottom flask, and then you connect it to a long tube. On the outside of the tube, you have a reflux condenser. Okay, you got cold running tap water that go through the whole tube so that the organic reactant, when it evaporates, it will condense back to the liquid and drop down to the round bottom flask. And then the process will continue until you get the final product. Okay, so that's the setup for heating under reflux. A quick revision. Now, let's go back to the mechanism part. Okay, so what's going to happen if we put alcohol with the hydrogen halide in this case? So the first step, the oxygen atom on the alcohol, because it has a lone pair, it can accept a proton from the hydrogen halide. Okay, so it will form this oxonium ion. Remember, when you form 3 bonds on the oxygen and it carry a positive charge on it, we call it oxonium ion. Okay, and then the bond between hydrogen and the halogen breaks, and it forms the, for example, Cl minus chloride ion or bromide ion. Okay, and then for different type of alcohol, it would take different routes. So let's take a look at the tertiary one. Okay, so that's a reactive intermediate we have. And if we have a tertiary alcohol, okay, and you can see this part, if I highlight it using yellow, this part is just a water molecule. And for tertiary alcohol, and for tertiary alcohol, this water molecule can just leave and then form the carbocation. And this carbocation here, since it has 3 alkyl groups next to it, these 3 alkyl groups can donate electrons towards this positively charged carbon atom. Okay, so it will make it less positively charged, so that's more stable. Okay, so this water molecule can just leave, and then you form this carbocation, and then this carbocation would just combine with the halide ion we have, and then form the haloalkane we want. Okay, but that's only for tertiary alcohol, because it got more alkyl group, it's more substituted, so the water molecule can just leave by itself. And for this one, that's the SN1 route. Okay, only one molecule is used to form that reactive intermediate. But for primary alcohol, take a look at this example. Okay, so for this one, if the water just leave, then we have this then we have a positive charge formed on this carbon. However, this carbon here only have one alkyl group that can donate electrons to stabilize the positively charged carbon. So it's very unstable and it's not favored. So this route would, if it still undergo SN1 route, okay, it will take a lot of energy input to do so. So it's not favored. So for primary alcohol, what's going to happen is the halide ion will attack the positive, will attack this carbon, and then it will form this bond and hence weaken the bond between the carbon and oxygen, so that the water molecule can finally leave. Okay, so forming this new bond will weaken the old bond. So finally, we will have the haloalkane and the water molecule here. So that's for primary alcohol. Primary alcohol would undergo SN2 mechanism. Okay. Okay, so again, if you still not sure about this, we have detailed explanation here, so you can read it later on. Okay, and similarly to that substitution, so previously we have PCl3 as the reactant, but now I want to introduce one more reactant to do the substitution. We can use PCl5, okay? Phosphorus pentachloride. Penta means 5, okay? So what's special about this reaction? So for this reaction, Again, we are going to form the haloalkane, but here we got some side product. So the first one is POCl3, okay, and this is in liquid state. And also we have HCl. Okay, this one is a gas. It's a hydrogen chloride gas. It's not hydrochloric acid. Okay, so this gas is a steaming fume, so you can actually observe it quite easily. Okay, so if we use an example here, that's the ethanol. So after the reaction, we should get chloroethane, and then we should also form POCl3 and also the HCl. Okay. Now, why I want to introduce this reaction? Because this reaction would take place at room temperature. That's due to the increased reactivity of PCl5 compared to PCl3. Okay, so this one is more reactive than PCl3. So this reaction can take place at room temperature. And also, it gives you an observable change. A steaming fume will be formed. Okay, so this is a good way to test for the presence of hydroxyl group, because you can easily do it under room temperature and you can see an observable change. Let me see if I can quickly play the video. Okay, so he is adding the PCl5 to the tube first. Okay, now he just put in the ethanol. Okay, and you can see the steaming fume produced. Okay, and then he further tested with the ammonia gas, and then you can see the white solid. The white solid is the ammonium chloride. Okay, so that's a way to test the hydroxyl group. Okay, and it will undergo at room temperature. Okay, so in here, that's the summary of these two types of reaction. First, we can react with hydrogen halide. And then secondly, we can react with PCl3. Okay, and all of this would need to be heated on the reflux to carry the reaction. And we also introduce one more way to make the haloalkane is to react with PCl5 pentachloride. Okay, and then for this one, it will undergo the reaction at room temperature. So we use it to test the presence of hydroxyl group. So the observable change is it forms a steaming fume. Okay, so take a look at this checkpoint question. So which of the following methods cannot produce 1-bromoethane? Take a look. The first one, ethane reacts with bromine under sunlight. Okay, so this reaction, if you still remember, That's the free radical substitution. And that's taught in Unit 27. Okay, you can refer it back. And then for part B, ethanol react with phosphorus tribromide. Okay, so this is the one that we just talked about, and it will undergo nucleophilic substitution. But that's what we learned in this unit. And then for part C, ethene react with hydrogen bromide. Again, we have learned this. That's the electrophilic addition reaction. Philic. Again, it's taught in Unit 27. So yes, your answer is correct. It should be D. Okay. Okay, so I think I will end this session here because we're running out of time. I will start a new one and let you to join. Yes, if you have any question up to this point, please raise it.